Tonight, we are traveling to the farthest edge of our planet, a boundary shaped by pressure rather than distance, where human presence becomes brief and fragile. The descent carries us into permanent darkness and rising force, an environment that allows no margin for correction and no guarantee of return. The ocean surrounds us so completely that it becomes easy to forget how little of it we have actually seen. Satellites trace its surface with confidence, and ships cross it without hesitation. Yet below those familiar waves lies a world that slips beyond direct observation. More than 80% remains unmapped, unseen, and never visited, not because it is distant, but because entry itself is uncertain. Depth changes the rules faster than our instincts allow. Pressure builds with every descending moment, turning metal fragile and reducing mistakes to final outcomes. Light fades until darkness becomes permanent, and communication weakens into scattered echoes that cannot always return. In space, danger is severe but stable. In the deep ocean, conditions change without warning. Scientists speak of this environment with restraint and care. Missions are described as fragile. Equipment is treated as temporary. Rescue is often theoretical rather than real. The sea does not lack curiosity directed toward it. It resists our presence through force, weight, and constant motion. But why does exploration fail more often beneath our own waters than beyond our atmosphere? What makes depth feel more forbidding than distance? How did vacuum become manageable while compression remained overwhelming? And why does the environment closest to us continue to turn us back? Tonight, we will ease into the comparison that scientists hesitate to dismiss. But before we begin, I would love to know where in the world you're listening from and what the time is there. It is always fascinating to think of these stories being heard across so many different skies. If you enjoy these gentle journeys into Earth's mysteries, please do consider leaving a like and subscribing to the channel. A warm thank you as well to those of you who are already subscribed. You're helping this little corner of the internet grow. Now take a deep breath, close your eyes, let your shoulders soften, and let's begin. Exploration did not always mean going farther away. Long before rockets and deep vehicles existed, it meant moving across a surface, following coastlines, tracing rivers, and stepping into spaces where the body could still orient itself against sky and land. The earliest maps were horizontal stories, shaped by walking, sailing, and sightlines that ended at the horizon. Progress became associated with reach rather than descent, with distance measured outward instead of downward. Depth remained an absence on the page, not because it lacked importance, but because it resisted being flattened into a path. As technology advanced, this inherited perspective quietly hardened into expectation. The sky offered clear reference points and predictable motion, while the ground beneath the ocean dissolved those anchors almost immediately. Space exploration emerged during a time when visibility, telemetry, and repetition aligned neatly with existing engineering instincts. Orbits could be calculated, environments could be simplified into variables, and success could be revisited again and again. The upward direction became a symbol not only of ambition, but of order, a place where difficulty could be isolated, studied, and gradually reduced. The ocean followed a different story. Early encounters beneath the surface revealed a space that punished intrusion without warning. Pressure did not scale gently, corrosion worked constantly, and motion never truly paused. These traits placed the deep ocean outside the narrative of steady advancement. It was categorized not as a frontier to be settled, but as a hazard to be survived. That distinction settled quietly into institutional thinking, shaping how missions were framed and how often they were attempted. Exploration below the waves became episodic rather than continuous, defined by brief visits instead of sustained presence. Funding patterns followed this logic with little resistance. Long term investment favored environments where infrastructure could persist and be reused. Space allowed platforms to remain in place, systems to be upgraded, and crews to return without rebuilding from nothing. The ocean demanded fresh effort every time, with vehicles exposed to wear even in success. Cultural attention followed the same current. Public imagination gravitated toward visible milestones, launches, landings, and anniversaries that could be marked in calendars. The deep sea offered fewer such moments, its achievements quieter and often unseen. Engineering choices reflected these priorities in subtle ways. Tools were designed for isolation rather than compression, for emptiness rather than weight. Training pathways, research institutions, and international partnerships grew around the assumption that exploration was best pursued, where conditions stayed stable enough to learn from repetition. Depth became an exception, something approached cautiously and sparingly. Over time, the comparison between space and ocean stopped feeling artificial. It became a mirror of our own habits, revealing not which environment was more dangerous, but which one aligned more easily with how humans learn to explore at all. Pressure announces itself long before it is seen or measured. It begins as an invisible accumulation, a quiet arithmetic written into the water itself. Each descending meter adds weight, not in a way that feels dramatic to the body, but in a way that compounds relentlessly. What intuition imagines as a gradual squeeze unfolds instead as an accelerating force, stacking upon itself faster than the mind expects. The ocean does not pause to acknowledge scale. It simply continues adding mass, layer by layer, until familiar materials begin to behave in unfamiliar ways. At modest depths, structures still resemble their surface selves. Metal holds its shape, seals remain intact, and systems respond as designed. Then a threshold is crossed, often sooner than anticipated. Pressure no longer acts as background stress, but as a defining presence. It presses inward from every direction at once, exploiting microscopic weaknesses that engineering can neither see nor fully predict. Bolts flex imperceptibly, housings deform by fractions of a millimeter, and those changes cascade forward. The environment does not signal danger in advance. There is no warning phase, only the moment when tolerance is exceeded. Failure beneath the surface rarely unfolds as a sequence. It arrives as an event. A seal gives way, a housing collapses, a joint ruptures under forces it was never meant to redistribute. The shift from intact to compromised happens faster than human reaction times, and often faster than automated systems can compensate. Unlike many environments where degradation offers clues, pressure erases the opportunity for adjustment. Once a boundary is crossed, the surrounding water does the rest of the work instantly and completely. This immediacy changes the nature of decision making. In places where gravity or temperature dominate, small corrections can stabilize a situation long enough for learning or retreat. In the deep ocean, correction presumes survival through the failure itself. Pressure allows no such margin. The moment integrity is lost, water occupies the space with decisive efficiency. The difference between operational and destroyed can be measured in seconds, sometimes less, leaving no interval for rescue or recovery. Because of this, depth becomes less about distance traveled and more about commitment. Every additional descent accepts a narrowing band of survivable outcomes. Systems are designed not to adapt, but to endure without change. Exploration therefore advances cautiously, step by careful step, constrained by the understanding that pressure does not negotiate. It enforces its limits without escalation or delay, turning the deep ocean into a place where missions are not ended by error, but by thresholds silently crossed. Emptiness sounds hostile, yet it is a kind of simplicity. In a vacuum, there is very little to push back. Objects carry their own boundaries with them, and forces act in predictable directions. When something fails in that environment, it tends to separate, drift, or slowly unravel. Motion follows straight lines, and damage reveals itself through visible change. The absence surrounding a structure does not actively interfere with it. It waits. Compression behaves in the opposite way. In the deep ocean, the surrounding water is not absence but presence, dense and unyielding, pressing inward at every surface. Structures exist in constant negotiation with that force, even when they appear motionless. The water does not simply surround an object, it leans into it. Every seam, curve, and joint becomes a meeting point between design and pressure, a place where balance must be held perfectly or not at all. Because of this, failure underwater takes on a different character. Materials rarely tear outward or drift apart. Instead, they fold, buckle, or collapse inward. The external force does the work, exploiting the smallest inconsistencies in thickness or alignment. A component can appear stable until the moment it is not, then disappear into itself as surrounding water occupies the space instantly. This form of failure leaves little evidence behind. What existed a second earlier becomes compressed debris, reshaped by the same force that caused the collapse. Engineering in a vacuum allows room for gradual response. Systems can register changes, vent excess pressure, or shed damaged components. Under compression, there is no excess to release. The force originates outside the system, beyond any internal control. Once pressure surpasses structural limits, the reaction is immediate and complete. There is no slow progression from damage to failure, only a sudden rearrangement of matter driven inward. This difference reshapes how environments are approached. A vacuum challenges survival but not form. It leaves structure intact as long as boundaries hold. Compression challenges form itself, turning architecture into a temporary arrangement maintained only by resistance. The ocean does not permit slack in this resistance. It applies force uniformly and continuously, leaving no direction to escape into. Movement offers no relief, and stillness offers no protection. Over time, this reality has shaped assumptions about manageability. Emptiness feels counterintuitive but learnable, governed by rules that remain stable once understood. Compression feels personal, active, and relentless, a condition that must be endured rather than mastered. The deep ocean becomes an environment where success is defined not by adaptation, but by how long structures can hold their shape against a force that never eases. Light does not fade gently as the ocean deepens. It thins quickly, filtered and scattered by water long before pressure becomes dominant. Within the upper layers, sunlight is already being divided, its wavelengths absorbed unevenly until color drains away in a precise sequence. Reds vanish first, then oranges and yellows, leaving behind a narrowed blue that grows dimmer with every meter. This transformation happens close to the surface, far sooner than most expect, turning brightness into a fragile and temporary condition. Below that boundary, illumination becomes an active effort rather than a natural state. Sunlight no longer reaches directly, arriving instead as a memory, diffused and weakened beyond usefulness. The ocean absorbs what remains with quiet efficiency. What appears clear from above resolves into shadow below, not because of obstruction, but because water itself becomes the barrier. Distance alone is enough to erase the sky. Artificial light enters this environment with limitations that are difficult to overcome. Beams flare outward, then collapse as suspended particles scatter photons in all directions. Instead of revealing space, light creates a narrow tunnel surrounded by immediate darkness that presses in from the edges. The brighter the source, the sharper this contrast becomes. Objects appear suddenly within range, then vanish just as quickly as the vehicle moves forward. Vision advances only a few meters at a time. This condition changes how exploration unfolds. Movement does not gradually reveal terrain. It replaces one small circle of visibility with another, never allowing a wider sense of place to emerge. Orientation relies on instruments rather than sight, and even those offer interpretations rather than images. The environment is present, but never fully disclosed. Navigation becomes an act of trust in systems that translate distance into data, while direct observation remains fleeting and incomplete. Darkness, at depth, is not the absence of light, but its defeat. Even powerful lamps struggle against absorption and scattering, their reach measured in moments rather than landscapes. Shadows dominate not because light is weak, but because the medium is relentless. The seafloor, when it appears, does so in fragments, textures emerging briefly before dissolving back into blackness as the vehicle passes. Because of this, the deep ocean resists being known through sight. Exploration proceeds without the reassurance of continuous visibility, guided by instruments and inference instead of horizons. Darkness establishes itself almost immediately, not as a dramatic threshold, but as a constant condition. It shapes every decision, limits every encounter, and ensures that much of what exists beyond the surface remains sensed rather than seen, present, but always just beyond the reach of light. Communication begins to falter almost as soon as water closes overhead. The ocean is not empty space carrying messages forward, but a dense medium that absorbs, bends, and breaks them apart. Signals that travel effortlessly through air find little purchase here. Radio waves, which form the backbone of distant communication above the surface, are quickly swallowed. Their energy dissipates into the surrounding water, fading into heat rather than information. What remains is silence that cannot be filled by strength alone. This limitation reshapes every aspect of deep exploration. Commands cannot be sent freely, and responses cannot always return. Long wavelengths penetrate only shallow depths, while higher frequencies vanish almost immediately. Communication becomes tethered to cables, relays, or brief surfaced moments. Once a vehicle descends far enough, it enters an environment where real-time conversation is no longer possible. Decisions must be made in isolation, carried out without confirmation, and trusted to unfold as intended. Sound offers an alternative, but not a solution. Water carries sound efficiently, yet not faithfully. Waves stretch and compress as they pass through layers of differing temperature and salinity, bending paths in ways that defy straight lines. Reflections arrive late or altered, overlapping with echoes from unexpected directions. Distance becomes difficult to judge, and origin becomes uncertain. What seems close may be far, and what feels distant may be directly below. As depth increases, these distortions compound. Currents introduce subtle motion. Seafloor features scatter signals unpredictably, and even the vehicle itself becomes a source of interference. Noise from machinery blends with environmental sound until meaning blurs. Listening requires interpretation rather than recognition. Communication shifts from exchange to inference, where data must be reconstructed rather than received clearly. Silence, in this context, carries weight. It does not announce failure with certainty. A missing signal can indicate obstruction, distortion, or complete loss. The absence of sound offers no explanation. Surface teams wait for confirmation that may never arrive, unable to distinguish between delay and disappearance. Time stretches, filled with static and uncertainty, while the ocean holds its answers without urgency. Because of this, exploration beneath the surface accepts isolation as a constant condition. Vehicles operate beyond continuous supervision, guided by preloaded instructions and assumptions about conditions that may already have changed. Communication becomes intermittent and fragile, something hoped for rather than relied upon. The ocean does not forbid signals entirely, but it refuses clarity. It allows messages only in fragments, shaped by water that prioritizes motion and density over transmission. In this environment, silence is not an exception. It is part of the landscape, present alongside pressure and darkness, quietly shaping how far exploration can truly reach. Orientation begins to soften the moment familiar reference points disappear. At the surface, direction feels inherited from the sky. Satellites mark position continuously, signals bounce cleanly between receivers, and location exists as a stable fact rather than a suggestion. Below the waterline, that scaffolding dissolves. GPS signals, stretched thin by distance even in air, cannot penetrate the dense layers beneath. Their paths end quickly, absorbed before they can inform anything moving below. Position stops being broadcast and becomes something that must be reconstructed. Without external fixes, navigation turns inward. Vehicles rely on internal measurements, counting rotations, estimating velocity, and stitching together a path from motion alone. These systems begin confidently, but they drift by nature. Tiny errors accumulate quietly, each correction built on the last approximation. Over time, the math remains precise while accuracy slips away. A machine can know exactly how far it has traveled and still be uncertain of where it is. Currents add another layer of subtle complication. They do not announce themselves with force, especially in the deep. They move as slow rivers within the water column, flowing steadily in directions that cannot always be sensed directly. A vehicle may appear stationary relative to its instruments while being carried sideways by invisible motion. This displacement happens gently, without vibration or resistance, shifting position without signaling that anything has changed. Because of this, movement and location separate. Progress along a planned route does not guarantee arrival where expected. A straight descent can curve without intention, guided by water that flows differently at each depth. Even hovering can become an illusion, as surrounding layers slide past one another at varying speeds. The seafloor, when it appears, may not align with predictions based on surface calculations made hours earlier. Navigation then becomes an exercise in reconciliation. Sonar outlines must be compared against maps that may be incomplete. Landmarks emerge briefly, then vanish behind as the vehicle adjusts course. Each correction introduces new assumptions, and each assumption narrows confidence further. Direction is no longer a fixed arrow, but a consensus formed from imperfect signals. Within this system, becoming lost does not require drama. It does not depend on storms or mechanical failure. It can occur through consistency alone, through steady motion guided by systems performing exactly as designed. The absence of absolute position allows uncertainty to grow unnoticed, turning exploration into a process of careful approximation. This is why underwater navigation feels less like traveling across space and more like negotiating with it. The ocean offers no grid to lock onto, no stable frame that holds still long enough to trust. Direction remains provisional, shaped by currents, calculations, and partial glimpses of terrain. In this environment, knowing where something is becomes an evolving estimate rather than a settled fact, and even careful journeys can drift quietly away from certainty. Every machine sent into the deep carries the quiet understanding that return is uncertain. Unlike vehicles that leave Earth's surface and enter an environment of relative simplicity, deep sea machines remain immersed in a medium that never rests. Water presses, moves, corrodes, and infiltrates continuously. From the moment a vehicle submerges, the ocean begins interacting with every exposed surface, turning time itself into a stressor. Corrosion is the most patient of these forces. Salt water works slowly, threading into microscopic imperfections, altering metals at a chemical level. Protective coatings dull, seals stiffen, and joints lose the precise tolerances they once held. This process does not announce itself. It proceeds invisibly between missions, during storage, and even while systems sit idle. By the time damage becomes measurable, it has often already reshaped how the vehicle will respond under stress. Leaks arrive less gradually. A seal that functioned perfectly during testing can fail after repeated exposure to pressure cycles and temperature changes. Materials flex minutely with each descent and ascent, movements too small to see, but large enough to weaken bonds over time. Eventually, water finds a path inward. Once inside, it does not behave as a contaminant that can be flushed out. It becomes an occupying force, altering buoyancy, disrupting electronics, and accelerating corrosion from within. Structural fatigue compounds these risks. Deep sea vehicles endure constant vibration from currents and their own propulsion. Each mission introduces new stress patterns as the craft maneuvers close to the seafloor or holds position in moving water. These loads are complex and uneven, different from the clean, repetitive forces experienced by spacecraft in orbit. Over time, stress concentrates at joints and corners, creating vulnerabilities that simulations struggle to predict fully. Recovery magnifies the consequences of failure. When a spacecraft malfunctions, it often remains trackable, visible against a predictable background. Deep sea vehicles can disappear into terrain that absorbs sound and light, leaving only silence behind. Even when location is known, retrieval may be impossible. Depth, distance from support vessels, and shifting seafloor conditions can turn recovery into a separate expedition, one that risks adding another machine to the tally. As a result, the ocean floor holds the remains of exploration attempts spanning decades. Cameras, landers, cables, and vehicles rest where they failed, shaped by corrosion and slow burial. They are not monuments in the traditional sense, but quiet markers of how demanding the environment remains. Each abandoned machine reflects a moment where engineering met limits imposed by water, time, and pressure working together. This accumulation gives the deep ocean its reputation as a graveyard of technology, not because of neglect or recklessness, but because the environment extracts a cost from every visit. Machines are permitted entry, but not permanence. Return is always conditional, negotiated through materials that must resist a world designed to wear them away. Human presence beneath the ocean unfolds on a borrowed schedule. Time does not pass there in the same way it does at the surface. Every moment spent at depth is measured against limits set not by endurance or intention, but by physics acting on the body itself. Pressure, gas exchange, and temperature combine to define windows that cannot be widened through will or experience. The body becomes a system temporarily tolerated by an environment that never truly accommodates it. As depth increases, that tolerance narrows sharply. Breathing mixtures must change, decompression profiles grow longer, and the return to the surface becomes as critical as the descent itself. Even when technology mediates these processes, it does not remove them, it only delays their consequences. The human body accumulates debt with every passing minute below, storing it in tissues that will later demand careful release. Time spent exploring must always be balanced against time required to leave safely. This creates a fundamental asymmetry. Arrival can be direct and decisive, but departure must be slow, staged, and exact. The deeper the mission, the more its structure bends around the necessity of ascent. Work at depth becomes brief by design. Tasks are compressed, observations prioritized, movements restrained. There is no concept of lingering. Presence is measured in minutes or hours, never in days that allow routines to form. Living beneath the surface would require rewriting these constraints. Continuous exposure would amplify physiological stress beyond manageable levels. Even protected habitats remain subject to pressure differentials, temperature gradients, and the logistics of maintaining breathable atmospheres. Resupply becomes complex, evacuation uncertain, and cumulative risk unavoidable. Unlike environments where gravity dominates, the deep ocean imposes its costs constantly rather than episodically. Because of this, exploration settles into a pattern of approach and withdrawal. Humans descend, observe within strict margins, then retreat upward to recover equilibrium. Each mission is framed as a visit rather than a stay. Knowledge is gathered in fragments, assembled later at the surface where reflection is safe and time is abundant. The rhythm never changes, no matter how advanced the equipment becomes. This recurring retreat is not a failure of ambition. It reflects an acceptance of limits that cannot be engineered away. The ocean allows entry but not habitation. It permits observation without consent to remain. Even the most carefully planned dives end with ascent as their defining act, returning the human body to an environment where pressure relaxes and time resumes a familiar pace. In this way, the deep ocean resists becoming a lived space. It remains a place humans pass through briefly, leaving as little trace as possible. Exploration advances through repeated departures rather than continued presence, shaped by the understanding that beneath the surface, endurance is temporary and retreat is not a setback, but the only sustainable conclusion. Reaching the deepest places on Earth has never been a matter of simple descent. It has required a convergence of rare conditions, precise engineering, calm seas, and a narrow window where everything functions exactly as intended. Even then, success arrives quietly. A vehicle touches the bottom, lingers briefly, gathers what it can, and begins the long return upward. The moment itself is small compared to the effort that made it possible. These locations sit at the limits of what materials and planning can tolerate. Pressure approaches values that reshape steel, darkness removes visual certainty, and distance isolates the mission from immediate support. Every descent carries a singular focus on survival through the visit. Redundancy is built in. Caution shapes every maneuver, and exploration unfolds slowly, step by careful step. There is little room for improvisation. The deep allows presence only under controlled restraint. When these depths have been reached, the accomplishment has carried symbolic weight. It proves that access is possible, that the boundary is not absolute, yet the impact on broader understanding remains modest. A brief visit reveals textures, measurements, and samples, but not context. The environment does not open itself fully to observation during such moments. It offers a glimpse rather than a portrait. This limitation is not due to failure of intent or capability. It arises from scale and isolation. The deepest parts of the ocean are not singular points, but vast regions shaped by slow geological forces and constant motion. One successful descent illuminates only the immediate surroundings, a small circle within an immense landscape. What lies beyond remains inferred, stitched together from indirect data rather than direct experience. The knowledge gathered from these dives is therefore narrow by necessity. Instruments record pressure, temperature, chemistry, and movement, but only along the path taken. Biological observations capture organisms encountered by chance rather than by survey. Geological samples reflect specific conditions rather than regional patterns. Each piece adds to a growing mosaic, yet the full image remains incomplete. Even repetition does not easily solve this. The difficulty and expense of reaching such depths limit how often missions can return. Conditions vary between visits, and exact routes are hard to replicate. Comparisons become tentative, constrained by differences in timing, location, and equipment. Progress accumulates slowly, advancing understanding in careful increments rather than sweeping revelations. As a result, the deepest point ever touched stands less as a conquered destination and more as a marker of restraint. It demonstrates where exploration reaches its narrowest aperture, where access exists but expansion remains difficult. The achievement is real, yet its influence spreads only so far. Beneath that point, the ocean continues outward in all directions, holding its complexity beyond the reach of brief encounters and reminding us that even when contact is made, comprehension remains partial. The ocean floor stretches outward in silence, wider than intuition suggests. It occupies more area than all continents combined, yet remains largely unvisited in any direct sense. Distance here is not a straight line, but a spread, an expanse unfolding in all directions beneath moving water. Even at modest resolution, this surface becomes vast, its features repeating and varying over scales that resist easy summary. To cover it completely would require time, measured not in missions, but in generations. Because of this scale, exploration has adapted by necessity. Instead of descending to sea, scientists often look from above. Satellites trace subtle changes in sea surface height, revealing gravitational signatures shaped by mountains and valleys far below. Ships tow instruments that send sound downward and listen for its return, translating echoes into contours. These methods create maps that are elegant and efficient, capturing broad structure without ever touching the ground they represent. This approach allows coverage where direct presence cannot. Large areas can be outlined in weeks that would take lifetimes to visit individually. Patterns emerge, ridges align, basins deepen, and margins take shape. From a distance, the seafloor begins to resemble a coherent landscape. Yet this coherence is abstract. It is composed of numbers, reflections, and inferred shapes rather than surfaces that have been seen or felt. The difference between mapping and seeing lies in resolution of experience, not accuracy of measurement. Data can describe height, slope, and composition, but it cannot fully convey texture, motion, or context. A ridge mapped by sonar does not reveal how sediment moves across it, how life settles into its crevices, or how currents shape its edges over time. These qualities require proximity, time, and observation that cannot be replicated remotely. As a result, much of the ocean floor exists in a kind of informational outline. Its form is known broadly, its details suggested rather than confirmed. Gaps remain not because of neglect, but because depth, distance, and access limit how often direct encounters can occur. Each descent fills in a small patch, adding clarity to one location while leaving countless others unchanged. Understanding grows unevenly through this process. Some regions become familiar through repeated study, while others remain blank beyond their basic geometry. The map expands, but comprehension advances more slowly, constrained by the difference between measured surfaces and lived environments. The ocean floor remains present in our models and datasets, yet absent from direct experience. In this way, blankness does not imply ignorance, but restraint. It reflects a choice shaped by scale and limitation, where knowing broadly becomes possible long before knowing deeply. The seafloor waits beneath its covering of water, defined in outlines and estimates, holding its finer details beyond the reach of maps alone. Nothing beneath the ocean remains still long enough to be claimed. Movement persists even where it cannot be felt directly, shaping space through slow, continuous motion. Currents travel through the water column like layered winds, flowing at different speeds and directions depending on depth, temperature, and chemistry. Some move quickly, others drift so gradually they seem absent, yet together they form a system that never truly pauses. These currents do more than carry water. They transport heat, sediment, nutrients, and living organisms across immense distances. A vehicle descending through this environment enters a shifting framework, one where position is constantly negotiated. Even when instruments report stability, surrounding layers may be sliding past each other, introducing motion without resistance. The ocean's movement is quiet, persistent, and difficult to isolate. This restlessness extends to the sea floor itself. What appears solid and permanent from afar is shaped continuously by forces above. Sediment settles and resettles, smoothed by gentle flows or rearranged by sudden pulses of energy. Fine particles travel like dust in air, burying tracks, softening edges, and filling depressions. Over time, these slow processes erase evidence of passage, leaving little trace that anything disturbed the surface at all. In some regions, the changes are subtle. A ridge maintains its form while its surface shifts imperceptibly. In others, movement is more decisive. Slopes collapse, channels migrate, and deposits spread unevenly after distant events send energy through the water. These transformations do not require dramatic triggers. They unfold naturally, driven by gravity and flow acting together over long spans. Because of this, maps capture only moments. They reflect conditions as they were during measurement, not as they will remain. A contour recorded one year may soften the next, altered by processes that leave no obvious signature until comparison reveals difference. Even precise charts become approximations over time, accurate in outline, but dated in detail. Exploration must therefore accept uncertainty as a constant companion. Routes plotted carefully can drift from expectations, landmarks shift, and reference points lose clarity. The ocean does not preserve paths or boundaries. It reshapes them gradually, ensuring that familiarity fades between visits. Each return requires fresh observation rather than reliance on memory. This perpetual motion complicates understanding. It blurs the line between stable features and transient ones, demanding caution in interpretation. What seems fixed may be in slow transition, and what appears unchanged may only be temporarily aligned. Knowledge becomes provisional, grounded in patterns rather than permanence. The ocean's movement is not chaotic, but it is continuous. It resists being frozen into a single description. Maps remain useful, but never final. Beneath the surface, the world is always adjusting itself, ensuring that yesterday's representation may already belong to the past. Sound becomes the ocean's primary means of expression, not by choice, but by elimination. Light has already surrendered, and signals carried by air have long since dissolved. What remains is vibration, pressure waves moving through water that accepts them readily. In this environment, sound travels farther than sight ever could, threading through darkness and distance with a persistence that feels almost conversational. Exploration depends on this persistence. Sonar sends pulses outward, listening for their return, building images from the time it takes echoes to arrive. Without it, the deep would be nearly featureless to human instruments. Valleys, ridges, and boundaries emerge through reflected sound, allowing vehicles to move without collision and scientists to sketch landscapes never directly seen. Sonar does not illuminate the ocean, but it outlines it. Yet sound in water does not behave simply. It bends as it travels, refracted by layers of temperature and salinity that shift constantly. A pulse that leaves its source straight can curve subtly downward or sideways, guided by invisible gradients. Echoes may arrive stretched or compressed, altered by the path they were forced to take. Distance and direction blur together, demanding interpretation rather than certainty. Scattering adds another layer of complexity. When sound meets uneven surfaces, suspended particles, or moving organisms, it breaks apart. Reflections multiply, overlap, and return from angles that no longer correspond neatly to their origins. A single feature can produce several echoes, each suggesting a different shape or location. Separating signal from artifact becomes an act of careful judgment rather than straightforward measurement. Within this system, sonar images acquire a dreamlike quality. Forms appear solid, then dissolve as perspective shifts. A ridge sharpens into view only to flatten as the vehicle moves closer. Shadows emerge that suggest objects where none exist, created by sound bending around empty water. These illusions are not errors in machinery, but natural consequences of translating vibration into vision. Because of this, sonar must always be read with restraint. It reveals structure without guaranteeing truth. Confirmation requires repeated passes, adjusted angles, and comparison with other instruments. Even then, ambiguity lingers. What seems distinct in one sweep may soften in another, reshaped by changing conditions between moments. The ocean speaks through sound, but not with a single voice. This reliance on an imperfect language shapes how knowledge forms. Maps and models emerge through accumulation, each layer refining or correcting the last. Certainty grows slowly, never fully detached from doubt. Sound allows access where nothing else can, yet it also reminds explorers that access does not equal clarity. In the deep ocean, sound carries meaning forward, but it does not simplify it. It offers outlines instead of surfaces, suggestions instead of confirmations. Through vibration and echo, the ocean communicates just enough to be navigated, while keeping its full form indistinct, expressed in a language that must always be interpreted with care. Life in the deep ocean did not announce itself with clarity. It emerged gradually through instruments that detected heat where none was expected, chemistry that hinted at metabolism without sunlight, and movement in places thought to be barren. These discoveries altered assumptions quietly. They suggested that life had found ways to persist beyond the reach of surface energy, sustained instead by the planet's internal processes. Ecosystems formed around chemical gradients rather than light. At vents and seeps, minerals released from Earth's crust mixed with cold seawater, creating energy sources invisible from above. Microorganisms learned to harness these reactions, building the foundation for complex communities. Larger organisms followed, assembling networks of dependence that functioned entirely apart from photosynthesis. The absence of sunlight did not signal absence of life, but a different set of rules governing it. This realization complicated exploration immediately. The deep ocean was no longer only a physical challenge, it became a biological one. Vehicles descending into these regions encountered environments shaped by delicate balances where temperature, chemistry, and flow maintained stability over long periods. Even small disturbances introduced change. Sediment clouds altered filtration, heat shifted circulation, and contact disrupted structures that had grown slowly over decades or centuries. Biology introduced unpredictability into missions designed for observation. Living systems respond, adapt, and recover on timescales that differ from mechanical ones. An area surveyed once might appear altered on a return visit, not because of error, but because life itself had changed in response to intrusion. Exploration ceased to be passive by default. Presence carried consequence. This awareness reshaped priorities. Scientists began to weigh the cost of contact against the value of data gained. Sampling became more conservative, and observation favored distance where possible. The goal shifted from extracting information to minimizing impact. In some places, exploration paused entirely, held back by uncertainty about long-term effects that could not be undone. Disturbance also carried ethical weight. Many deep-sea ecosystems exist nowhere else, confined to narrow conditions that cannot be replicated easily. Damage to these systems may be irreversible within human timescales. Recovery, if it occurs at all, unfolds slowly, measured in generations rather than seasons. What is altered by a single mission may remain changed long after instruments have returned to the surface. As life reshaped understanding of the deep, it added another layer of restraint. The ocean was not only resisting exploration through pressure, darkness, and distance, but through complexity that demanded care. Knowledge now required patience, repetition, and humility. The discovery of life where none was expected expanded the frontier, but it also narrowed the path forward, reminding explorers that what lies beneath the surface is not empty, but inhabited by systems that must be approached without haste. Fragility beneath the surface reveals itself not through dramatic collapse, but through quiet persistence. Small actions can leave marks that do not fade quickly, because recovery moves at a different pace below. Water slows processes that rely on circulation and light, and many deep environments remain stable for long stretches of time. When that stability is altered, the change can linger, reshaping conditions long after the disturbance has passed. A single contact can be enough. The touch of a vehicle, the wash from a thruster, or the settling of displaced sediment can shift balances that took centuries to establish. Fine particles may remain suspended longer than expected, drifting into surrounding areas and altering how organisms feed or breathe. Chemical gradients can be disrupted, changing the availability of energy that supports entire communities. Even brief exposure can initiate cascades that continue unseen. These effects are often subtle. There may be no immediate sign of harm, no visible damage that registers during a mission. Yet the deep ocean records change patiently. Structures built slowly by biological or geological processes do not reassemble quickly once broken. Growth rates are measured in years rather than months, and some systems may not recover within any human time frame. Absence of visible impact does not imply absence of consequence. Because of this, exploration has learned restraint. Direct contact is limited whenever possible. Instruments are designed to observe from a distance. Sampling is reduced to essentials, and repeated visits are approached cautiously. The objective shifts from access to preservation, recognizing that understanding gained at the cost of degradation is incomplete. Knowledge that diminishes its subject carries an inherent limitation. Ethical considerations enter quietly but firmly. Scientists weigh the value of new data against the potential for lasting change. Some locations are approached only once, documented carefully, then left undisturbed. Others are designated as reference sites, preserved to allow comparison with altered regions. These decisions slow exploration, but they also deepen it, embedding responsibility into the act of discovery. Boundaries emerge, not as prohibitions, but as agreements shaped by humility. The deep ocean is not an empty archive waiting to be opened. It is an active system, sensitive to interference and slow to respond. Ethical limits recognize that exploration is not neutral and that observation itself is a form of interaction. In this way, fragility becomes part of the environment's character. It does not announce itself loudly, but it informs every choice made below the surface. Progress unfolds deliberately, paced by an awareness that some changes cannot be undone. Exploration continues, but with a measured touch, guided by the understanding that preserving what exists is as important as uncovering what is unknown. Loss of contact rarely arrives as a sudden event. It begins as a pause, a delay measured in seconds that stretch longer than expected. Telemetry flickers, data packets arrive incomplete, and familiar rhythms fall out of sequence. At first, the absence feels technical, something that can be corrected through patience or recalibration. Then the pause lengthens, and the connection does not return. When a vehicle stops responding, the ocean offers no immediate explanation. Power may still be present, systems may be intact, and motion may continue unseen. The surface receives nothing to confirm or deny these possibilities. Without continuous communication, interpretation replaces certainty. Engineers replay the last received signals, searching for patterns, while the vehicle itself remains embedded in an environment that does not relay its condition. As time passes, options narrow. Commands sent into the water vanish without acknowledgement. Cables, if present, may have failed silently. Autonomous protocols may still be running, or they may have been interrupted by conditions that left no trace. The gap between surface and depth grows wider, filled by assumptions rather than information. The ocean does not clarify what has occurred. Recovery becomes difficult not through lack of intent, but through physical reality. Vehicles often operate at depths where retrieval requires another mission as complex as the first. Precise location may be uncertain, shifted by currents or obscured by terrain. Sound searches can suggest possibilities, but resolution remains limited. Even when a signal is detected, reaching it may exceed the capacity of available equipment. Time works against recovery efforts. Currents continue to move, sediment continues to fall, and corrosion continues its slow work. Evidence degrades steadily. Tracks left during descent soften, debris settles into surrounding textures, and recognizable forms lose definition. The ocean integrates what remains into its background with quiet efficiency. In many cases, search operations are brief by necessity. Resources are finite, conditions unpredictable, and repeated exposure adds risk without guaranteeing success. Decisions are made to preserve future exploration rather than exhaust it on uncertain retrieval. Vehicles become part of the seafloor, their final states inferred rather than observed. This pattern has shaped how missions are planned. Redundancy increases, autonomy improves, and loss is accounted for without expectation of reversal. Designs emphasize data transmission over physical return, prioritizing knowledge that can escape even if hardware cannot. Exploration adapts to the understanding that some endpoints will remain unresolved. The ocean's ability to erase evidence is not aggressive. It unfolds gradually, through motion, chemistry, and time acting together. What disappears does not vanish instantly, but it becomes indistinct, then contextualized as part of the environment rather than a record of human presence. Contact fades, recovery slips beyond reach, and the deep resumes its continuity, holding the story without revealing its conclusion. Rescue in the deep ocean unfolds within boundaries that narrow almost immediately. Unlike environments where assistance can approach gradually, depth imposes limits that begin counting down from the moment something goes wrong. Pressure, gas balance, and structural integrity all define windows that cannot be expanded by urgency. Time becomes a fixed quantity, not something that can be negotiated through speed or effort. Those limits shape every contingency. Vehicles and habitats are designed with margins that assume prompt resolution or rapid ascent. Beyond those margins, survival depends on conditions aligning perfectly. Pressure constrains how long systems can remain intact after failure, and how long the human body can tolerate abnormal environments, even with protection. These constraints are not flexible. They persist regardless of preparation, weather, or available resources. Distance compounds the problem. Deep sea operations unfold far below the reach of immediate surface support. Between a distressed vehicle and help lies a column of water that must be traversed carefully. Descent alone takes time, often hours, even before rescue attempts can begin. Support vessels may be days away, and repositioning them requires coordination that unfolds slowly. The ocean does not allow shortcuts through its depth. Communication delays add further friction. Information about a problem may arrive incomplete or late, and confirmation of conditions below may remain uncertain. Decisions must be made with partial knowledge, increasing caution rather than speed. Equipment must be prepared, tested, and deployed in sequence, each step dependent on the last. The process favors precision over haste, even when urgency is understood. Once a rescue vehicle begins its descent, conditions continue to limit possibility. Pressure restricts how rapidly movement can occur. Navigation uncertainty complicates rendezvous, and changing currents may alter expected positions. Even a successful approach does not guarantee resolution. Docking under pressure requires alignment within narrow tolerances, and any miscalculation risks compounding the emergency rather than relieving it. These realities explain why rescue often remains theoretical. Plans exist, protocols are refined, and drills are conducted, yet execution depends on variables that resist control. The deep ocean allows little margin for overlapping failures. Time available for intervention may expire before equipment reaches depth, or before conditions allow safe engagement. Because of this, missions are planned with the assumption that external help may not arrive in time. Systems emphasize autonomy, redundancy, and self-resolution rather than reliance on rescue. This philosophy does not dismiss the value of preparation. It reflects an understanding of environment rather than a lack of care. The ocean does not prevent rescue through hostility. It does so through scale and constraint. Distance stretches timelines, pressure enforces limits, and motion complicates every approach. Help may be possible in principle, yet inaccessible in practice. In this environment, safety depends less on the promise of arrival and more on design choices made long before anything goes wrong. Human error does not change character beneath the ocean, but its consequences do. Small deviations that would be recoverable elsewhere accumulate weight as depth increases. A valve turned slightly too late, a calibration offset by a fraction, or a timing mismatch measured in seconds can cascade quickly. The environment does not amplify mistakes through drama, but through compression. There is less space, less time, and fewer paths back to equilibrium. Margins narrow as systems descend. At the surface, redundancy absorbs inconsistency. Multiple checks overlap, and corrections can be layered gradually. In the deep ocean, those layers thin. Pressure constrains materials. Darkness constrains perception, and distance constrains communication. Each safeguard still exists, but their tolerance shrinks. When one element slips, it leans immediately on the next, which may already be operating near its limit. This compression alters how error unfolds. Problems rarely announce themselves clearly. Signals may be incomplete or delayed, and visual confirmation may be unavailable. A minor anomaly can resemble routine fluctuation until it crosses a threshold. By the time the shift is recognized, options may already be limited. Response becomes reactive rather than adaptive, shaped by what remains possible rather than what would be ideal. Training accounts for this as much as it can. Crews rehearse procedures repeatedly, learning to recognize patterns and respond calmly under constraint. Simulations, model failure modes, and protocols are refined to reduce reliance on instinct alone. Yet training operates within abstraction. It cannot fully replicate the layered pressures of real depth, where systems age, conditions drift, and variables intersect in unique ways. Experience improves judgment, but it does not erase uncertainty. Each mission combines familiar elements in unfamiliar configurations. The ocean introduces subtle changes that evade anticipation. Temperature gradients shift, currents alter alignment, and equipment responds differently after repeated exposure. Even experienced operators encounter situations that fall between rehearsed scenarios, requiring decisions without precedent. Because of this, error remains part of the equation, not as negligence, but as limitation. Humans bring adaptability and insight, but also rely on perception and timing that can be distorted by isolation and fatigue. Depth magnifies these distortions quietly. The body processes information under strain, and cognition adjusts to narrowed sensory input. Attention becomes focused, sometimes too narrowly, as broader context fades. The deep ocean does not forgive or punish error. It responds consistently, applying the same forces regardless of intent. When a mistake aligns with a critical boundary, outcome follows without delay. This reality does not negate the value of training. It clarifies its role. Preparation reduces risk, but it cannot dissolve it entirely. Exploration continues within this understanding. Systems are designed to anticipate human fallibility, and missions are planned with conservative assumptions. Progress advances through caution rather than bravado. At depth, error is not exceptional. It is expected, accounted for, and managed where possible, yet never fully removed. The ocean ensures that human limits remain visible, shaping exploration through restraint rather than conquest. The mind adjusts to environment long before the body reaches its limits. In the deep ocean, that adjustment begins quietly, shaped by what is missing rather than what is present. Sight narrows first, reduced to instrument readouts and brief, illuminated fragments. Sound loses context, becoming signals without clear origin. Touch remains mediated through controls and pressure, separated from the surrounding world by layers of material. Sensory input thins, and with it, the constant feedback that anchors awareness. This reduction changes perception of time. Without natural cues, minutes stretch or compress unpredictably. Tasks feel suspended in a continuous present, unmarked by sunrise or horizon. Attention turns inward, focused on process and procedure, while the external world recedes into abstraction. The deep becomes less a place than a condition, defined by absence and restraint rather than landscape. Isolation compounds this effect. Missions unfold far from ordinary social reference points, often with limited communication and delayed responses. Even when contact is maintained, it lacks immediacy. Voices arrive filtered or intermittent, stripped of gesture and nuance. The sense of shared space dissolves, replaced by parallel experiences unfolding at different depths. The crew remains physically close, yet psychologically enclosed within narrow roles and responsibilities. Confinement intensifies awareness of these boundaries. Movement is restricted, posture fixed, and routine dictated by equipment. There is little room for spontaneity or distraction. The environment offers no neutral space where attention can drift. Every surface carries function. Every sound suggests system status. Rest and work blur together, separated only by schedule rather than context. These conditions place steady pressure on cognition. Focus must be maintained without relief, and small irritations can grow disproportionate in confined settings. Fatigue alters judgment subtly, influencing reaction time and interpretation. The mind compensates through discipline and training, yet compensation itself requires effort. Depth does not provoke a sudden psychological break. It applies a constant load, one that accumulates through duration rather than intensity. Because of this, missions remain short by design. Limits are set not only by engineering or physiology, but by the understanding that prolonged exposure alters mental performance in ways difficult to measure precisely. The goal is clarity, not endurance. Short visits preserve decision making, situational awareness, and the ability to respond flexibly to unexpected conditions. Extended presence would require buffering these effects through space, variety, and sensory richness that depth does not provide easily. Until such environments can be sustained reliably, exploration accepts brevity as a safeguard. Descent becomes a focused interval of observation and return, bounded to protect both body and mind. The psychological weight of the deep does not manifest as fear or panic. It emerges as quiet narrowing, a gentle compression of experience. Awareness becomes precise but constrained, effective but taxed. By limiting time spent in this state, exploration maintains balance, allowing knowledge to surface alongside those who gathered it, intact and able to be understood. Progress in the deep ocean advances in measured steps rather than sweeping strides. Each mission represents a convergence of planning, funding, and opportunity that cannot be repeated easily. Vessels must be outfitted, crews assembled, equipment tested, and weather aligned. The margin for error is narrow, and preparation absorbs months or years before a single descent begins. When a mission finally occurs, it carries the weight of its rarity. Cost shapes this rhythm quietly but decisively. Deep sea exploration depends on specialized ships, custom vehicles, and teams trained to operate within extreme constraints. Maintenance continues between missions, and failures often require redesign rather than repair. Resources are concentrated into a small number of attempts, each expected to justify its expense through careful outcomes. The result is a pace defined by caution, where ambition is balanced against sustainability. These missions often function as single use moments. A descent may occur only once to a specific location, gathering data that cannot be expanded immediately through repetition. Conditions change, budgets shift, and priorities evolve before return becomes possible. What is learned must stand on its own for long periods, contextualized later through comparison rather than confirmation. Exploration unfolds as a series of isolated chapters rather than a continuous narrative. This structure favors incremental knowledge. Measurements refine models, observations adjust assumptions, and samples add detail to broader patterns. Each contribution is small, yet precise, fitting into an expanding framework built over decades. The deep ocean does not yield dramatic revelations frequently. Instead, it offers consistency, allowing understanding to mature through accumulation rather than surprise. Breakthroughs still occur, but they are rarely sudden. They emerge when enough fragments align to suggest something new, often long after the original data was collected. Interpretation continues at the surface, where time and collaboration allow insight to deepen. Progress becomes reflective as much as exploratory, shaped by patience rather than momentum. The contrast with other fields of exploration is subtle. Environments that permit frequent access encourage rapid iteration and visible milestones. The deep ocean resists that pattern. Each return requires rebuilding context, recalibrating expectations, and accepting that much remains unchanged since the last visit. Familiarity grows slowly, anchored in respect for limits rather than mastery over them. This pace influences perception. The absence of constant updates can appear as stagnation, yet the underlying record shows steady advancement. Maps become clearer, processes better constrained, and questions more precisely framed. Progress may be quiet, but it is persistent. In the deep ocean, speed is not the measure of success. Exploration honors endurance through restraint, allowing knowledge to accumulate without forcing conclusions. Each mission contributes a careful stroke to a picture still forming, shaped by time, scarcity, and the understanding that some environments reveal themselves only when approached slowly enough to listen. Repetition becomes possible when motion settles into rhythm. Above Earth, movement follows paths that change slowly, guided by gravity that behaves with remarkable consistency. Objects placed into orbit trace the same routes again and again, circling along corridors that can be calculated years in advance. This stability transforms travel into routine. Location becomes a pattern rather than a guess. Within these patterns, infrastructure accumulates. Platforms remain aloft, returning overhead predictably, allowing crews and equipment to rendezvous without rediscovering position each time. Vehicles are designed to dock, resupply, and depart along familiar trajectories. Systems are tested, adjusted, and reused, building continuity across missions. Each return strengthens understanding rather than resetting it. Predictability shapes engineering choices. Temperatures fluctuate within known bounds. Radiation can be shielded against consistently, and mechanical wear follows expected curves. Failures tend to be gradual and diagnosable, offering time for response. The environment does not press inward from all sides or shift terrain beneath a structure. It remains largely the same from one pass to the next, allowing lessons learned to remain relevant. This consistency invites iteration. Experiments can be repeated under similar conditions, refining results through comparison. Modifications can be tested incrementally, with confidence that changes in outcome reflect design rather than environment. Over time, procedures become standardized, and operations gain efficiency through familiarity. Progress compounds, built on the assumption that tomorrow will resemble yesterday closely enough to matter. Reusable infrastructure reinforces this cycle. Hardware does not need to be rebuilt entirely for each mission. Launch systems, modules, and support networks evolve rather than restart. Investment carries forward, amortized across years of use. Knowledge gained from one mission feeds directly into the next, accelerating development without increasing exposure proportionally. The psychological effect mirrors the physical one. Crews operate within contexts that feel continuous, supported by shared reference points and steady communication. Training aligns closely with reality, reducing surprise. Confidence grows through repetition, not bravado, allowing attention to shift from survival to exploration. This does not render space benign. It remains unforgiving in its own ways, demanding precision and respect. Yet its hostility is stable. Once understood, it can be planned around with confidence that conditions will not change suddenly between visits. That reliability creates an environment where repetition is not only possible, but expected. In contrast to the ocean's variability, space rewards return. Each pass along an orbit reinforces what was learned before, deepening familiarity through exposure rather than erasing it. Exploration advances through accumulation, supported by paths that remain open and systems designed to endure. Repetition becomes the engine of progress, driven by an environment that allows motion to settle into dependable patterns and invites understanding to build upon itself. Engineering reflects the character of the place it is built for. In space, that character is defined by stillness. Once free of atmosphere, structures exist in an environment where nothing touches them unless it is intended to. Motion follows predictable arcs, forces arrive from known directions, and absence dominates interaction. Objects persist unchanged unless acted upon, allowing designs to focus on balance, insulation, and control rather than defense. This stillness simplifies endurance. Materials age slowly when shielded from direct radiation, and temperature swings are anticipated. Surfaces remain clean, joints remain dry, and systems experience stress in repeatable cycles. Engineers can isolate variables and design responses that remain valid over long spans of time. Stability becomes a partner rather than an opponent. The ocean presents a different relationship entirely. It is never still, even when it appears calm. Water moves constantly, carrying dissolved salts, suspended particles, and biological material that interact with every surface they contact. Structures placed within it are not merely surrounded, but engaged continuously. Pressure presses inward, chemistry reacts outward, and motion introduces vibration and fatigue from the moment of submersion. Corrosion begins immediately. Salt water penetrates coatings, reacts with metals, and accelerates wear through electrochemical processes that never pause. Seals swell and stiffen, lubricants wash away, and materials weaken gradually until they no longer behave as designed. These changes are not isolated events. They compound over time, interacting with pressure cycles and thermal shifts to reduce tolerance across entire systems. Movement intensifies this strain. Currents introduce uneven forces that vary with depth and direction, bending structures in subtle ways. Vehicles experience constant micro-adjustments as they resist drift, placing repeated stress on thrusters and joints. Unlike space, where motion is deliberate and minimal, the ocean demands continuous correction. Energy is spent simply maintaining position. Designs that succeed in static environments struggle here. Components optimized for precision lose alignment under vibration. Electronics sealed carefully at the surface face leaks after repeated compression. Materials selected for strength reveal vulnerability when exposed to chemistry and motion together. Failure rarely traces back to a single flaw. It emerges from accumulation, where small stresses align over time. Because of this, underwater engineering prioritizes resilience over longevity. Systems are expected to age quickly, to endure rather than persist unchanged. Redundancy compensates for degradation, and missions are planned within shorter operational lifespans. Even the most robust designs accept that performance will decline with exposure. This contrast explains why failure arrives sooner beneath the surface. The ocean does not wait for use to begin its work. It interacts constantly, applying pressure, motion, and corrosion in combination. Engineering there becomes an exercise in managing decay rather than preventing it. Structures survive by resisting chaos briefly, not by escaping it, shaped by an environment that remains active long after human presence withdraws. The deep ocean does not present its challenges one at a time. Its defining trait is convergence. Pressure, motion, darkness, and chemistry do not operate independently below the surface. They overlap continuously, each amplifying the effects of the others. What appears as a manageable condition in isolation becomes far more demanding when layered together. The environment behaves less like a backdrop and more like a participant. Pressure shapes structure constantly, narrowing tolerances and reducing flexibility. Motion introduces variability, shifting forces unpredictably across surfaces already stressed. Darkness removes visual confirmation, increasing reliance on systems operating near their limits. Corrosion works quietly within this framework, weakening materials while other forces remain active. None of these processes pause to allow recovery. They proceed simultaneously, compressing time and choice. This convergence creates multiple failure points that exist at once rather than in sequence. A compromised seal may allow water ingress, while vibration loosens fasteners nearby. Electrical systems already contending with moisture experience stress, just as navigation drifts slightly off course. Each issue alone might be contained. Together, they interact in ways that accelerate decline. The system does not fail step by step, it unravels through alignment. Under these conditions, redundancy loses some of its protective power. Backup systems share the same environment and often the same vulnerabilities. When pressure flexes a housing, it affects primary and secondary components alike. When corrosion advances, it does so across connections rather than single parts. Cascades form naturally, not because design is poor, but because the environment treats systems as unified bodies rather than isolated elements. This is why collapse underwater feels sudden. There is rarely a single triggering event. Instead, limits are crossed in several places at nearly the same moment. Detection lags behind reality as sensors struggle to distinguish cause from symptom. Response windows close quickly, not due to error, but because multiple thresholds are reached together. The ocean does not require precision to cause failure. It only requires persistence. Designs account for this as much as possible. Engineers distribute loads, isolate components, and plan for degradation. Yet interaction remains difficult to model fully. Motion patterns vary. Chemical exposure changes with depth and time, and pressure cycles accumulate unpredictably. Small differences in conditions can shift how forces combine, producing outcomes that resist simulation. Because of this, systems underwater are evaluated not only for strength, but for how they fail. Graceful degradation becomes a goal, though it is not always achievable. When collapse occurs, it often does so across domains simultaneously: mechanical, electrical, and structural losses reinforcing one another. Recovery then becomes impractical, not because one component failed, but because the system as a whole transitioned abruptly from operational to inert. This behavior gives the ocean its reputation as an active opponent, not in the sense of intent, but through combination. Its forces align naturally, pressing together until resilience is exceeded. Exploration proceeds within this understanding, recognizing that survival depends less on eliminating individual risks than on managing how they intersect. In the deep, challenge is not singular. It is collective, and it arrives all at once. Information from the deep ocean often arrives without a picture to accompany it. Instead of landscapes and continuous observation, exploration returns with streams of measurements recorded by instruments operating alone in darkness. Sensors log temperature, pressure, chemistry, and motion faithfully, translating the environment into columns of values. These records are precise, yet detached, offering clarity without immediacy. This reliance on instruments reshapes perception. Observation becomes indirect, mediated through devices designed to survive conditions humans cannot. Cameras, when present, reveal only fragments within narrow fields and often operate briefly. More frequently, data arrives without any visual reference at all. The ocean is sensed rather than seen, described through fluctuations and trends rather than form. Numbers excel at capturing change, but they do not always convey cause. A spike in temperature suggests activity, yet does not show its shape or source. Variations in chemistry imply interaction, but not arrangement. Motion recorded by instruments outlines flow patterns without revealing what they pass through. The environment leaves signatures that must be assembled into meaning later, away from the place where they were created. This separation creates gaps that interpretation must bridge. Scientists compare datasets across time and location, layering context gradually. Models grow more refined as patterns repeat, yet uncertainty remains. Without direct observation, assumptions must stand in temporarily, tested against consistency rather than confirmed by sight. Understanding advances through inference, careful and provisional. The absence of visuals also limits intuition. Human perception relies heavily on spatial awareness, recognizing relationships through form and scale. When those cues are missing, cognition shifts toward abstraction. The deep ocean becomes conceptual, represented by graphs and simulations rather than scenes. Familiarity grows slowly, built through repetition of data rather than experience of place. This does not diminish the value of the information gathered. Instrumental data provides access where direct presence is impossible. It captures processes unfolding continuously, far beyond the duration of any mission. Long-term records reveal rhythms invisible to brief visits, documenting change across seasons and years. Yet interpretation always carries a distance, shaped by what cannot be observed directly. As a result, knowledge from the deep retains a tentative quality. Conclusions are framed carefully, aware of the limitations imposed by incomplete context. Confidence increases with convergence, when multiple instruments agree, when patterns align across regions. Still, the picture remains partial, missing the continuity that only sustained observation can provide. In this environment, understanding becomes an act of assembly. Data points are connected gently, allowing meaning to emerge without forcing coherence. Gaps are acknowledged rather than filled prematurely. The deep ocean speaks through instruments, offering signals that require patience to interpret. What is known is precise, yet bounded, shaped by numbers that describe faithfully while leaving much unseen, waiting beyond the reach of measurement alone. Scale defines the deep ocean more decisively than any single hazard. Its expanse spreads outward beneath the surface, uninterrupted by borders or landmarks that might compress it into familiarity. Even when technology reaches depth successfully, it does so at a single point, touching a surface that extends far beyond the limits of that encounter. Presence remains local, while the environment remains vast. This imbalance shapes everything that follows. Vehicles descend along narrow paths, survey limited corridors, and return with knowledge drawn from a small fraction of what exists. The reach of exploration remains constrained not by ambition, but by geometry. Each mission occupies a thin thread in a space measured in millions of square kilometers. Coverage accumulates slowly, unable to keep pace with the breadth it seeks to describe. As a result, exploration becomes an exercise in sampling. Sites are chosen carefully, informed by models and indirect data that suggest where significance may lie. What is observed stands in for what cannot be visited, forming proxies rather than comprehensive views. A ridge examined closely suggests others like it elsewhere. A community documented at one vent hints at similar systems nearby. Understanding grows through analogy, not through completeness. Sampling carries inherent uncertainty. Even representative sites cannot capture full variation. Conditions change with depth, latitude, and geological history, creating diversity that resists uniform description. Small shifts in chemistry or flow can produce different outcomes across short distances. A single descent may reveal complexity, yet it cannot define its boundaries. This reality leaves much unseen by necessity. The majority of the ocean floor remains outside the narrow windows where instruments and vehicles have passed. It exists in outlines traced by sonar, inferred by gravity, or suggested through scattered measurements. These methods reveal structure without intimacy, shape without texture. They provide context, but not experience. The unseen does not imply unknowable. Over time, patterns emerge as samples accumulate, correlations strengthen, models improve, and confidence grows in broad processes at work. Yet gaps persist between these islands of certainty. The space between them remains largely untouched, holding variations that may challenge existing assumptions when encountered. No single innovation has solved this scale problem. Increasing depth capability does not widen coverage. Faster vehicles do not multiply time at the seafloor meaningfully. Even coordinated efforts remain bound by cost, logistics, and endurance. The ocean's size continues to outpace the tools designed to explore it directly. Because of this, exploration proceeds with humility. Knowledge advances through careful accumulation rather than exhaustive survey. Each mission contributes a small piece, valuable but incomplete. The deep ocean remains largely unseen not due to neglect, but due to proportion. Its scale demands patience, accepting that much will remain beyond immediate reach, waiting quietly beneath the water as understanding continues to grow around it. Scientific writing about the deep ocean carries a distinctive restraint. The language is measured, sentences weighted with qualifiers that reflect conditions far removed from continuous observation. Descriptions avoid absolutes, favoring terms that allow room for revision. This careful phrasing is not stylistic preference. It is an adaptation to an environment where evidence arrives fragmented and context remains incomplete. Reports from deep sea research often rely on verbs that suggest possibility rather than certainty. Features are inferred, patterns suggested, and processes proposed within defined bounds. Measurements are precise, yet conclusions remain provisional. Each statement is anchored to the conditions under which data was collected, acknowledging that a different moment or location might yield another outcome. The tone reflects a landscape that resists being fully fixed in words. Uncertainty is treated as information rather than weakness. Confidence intervals, error margins, and model assumptions are woven into narratives that aim to describe without overstating. This emphasis signals respect for what remains unknown. It recognizes that instruments sample selectively, that visibility is limited, and that many processes unfold beyond the reach of direct confirmation. Absence of evidence is not presented as evidence of absence. Such care also reflects collaboration. Findings from the deep are built across disciplines, each contributing partial insight. Geophysics, chemistry, and biology intersect, yet rarely align perfectly. Language becomes the place where these perspectives meet cautiously, allowing differences to coexist without forcing resolution. Reports preserve ambiguity where reconciliation is premature, leaving space for future work to refine understanding. Quiet admissions of limit appear throughout this writing. Phrases acknowledge gaps, note restricted coverage, and emphasize that observations represent specific conditions rather than universal states. These acknowledgments are not disclaimers added at the end. They are integrated into the structure of the work itself. The reader is guided gently through what can be said, and equally through what cannot yet be concluded. This restraint shapes public perception slowly. Dramatic claims give way to accumulation, where understanding advances through convergence rather than announcement. Over time, repeated cautious statements build confidence through consistency. What is described tentatively across many studies gains solidity not through forceful language, but through agreement across independent lines of evidence. The deep ocean requires this approach. Its scale, variability, and inaccessibility impose humility on interpretation. Scientists speak carefully because they have learned that clarity emerges gradually. Language becomes an instrument of respect, preserving fidelity to data without extending beyond it. Precision is maintained not by certainty, but by alignment between claim and evidence. In this way, careful speech does not slow progress, it sustains it. By resisting the urge to finalize understanding too quickly, scientific writing leaves pathways open. The deep ocean remains complex, yet intelligible within bounds set by evidence. Each report adds a quiet layer to collective knowledge, shaped by restraint that mirrors the environment it seeks to describe. Large portions of the deep ocean remain defined more by absence than by description. Beneath mapped outlines and inferred structures lies terrain that has never been directly encountered. Slopes, plains, and fractures extend beyond the paths of vehicles, shaped by forces that continue without witness. The seafloor exists not as a single landscape, but as a mosaic assembled from fragments, with many pieces still missing. Within this unseen terrain, form and variability remain uncertain. Subtle features may guide currents or trap sediments in ways not yet recognized. Steep gradients can appear suddenly, altering circulation and chemistry over short distances. Even where broad shapes are known, fine scale structure often remains unresolved. Texture, composition, and change over time linger beyond observation, held in darkness that preserves their anonymity. Ecosystems also exist beyond familiar reference points. Life has been confirmed in unexpected places, yet the full extent of its distribution remains unclear. Communities may thrive in isolation, shaped by local conditions that do not repeat elsewhere. Some may be sparse and transient, others stable and complex. Without sustained presence, their rhythms remain largely speculative, inferred from limited encounters separated by long intervals. Many organisms likely remain undocumented, adapted to pressures and chemistries rarely sampled. Their interactions, lifespans, and roles within broader systems are difficult to determine when observation is brief. Patterns of migration, reproduction, and succession unfold on scales that resist capture by short missions. Biology in the deep continues its processes quietly, often leaving only indirect traces in the data collected. Beyond terrain and life, fundamental processes remain only partially measured. Heat transfer through the crust, chemical exchange between rock and water, and energy flow across ecosystems proceed continuously. Instruments capture portions of these dynamics, yet comprehensive understanding requires integration across time and space that remains challenging. Variability complicates interpretation as systems respond to subtle shifts that may not be detected directly. Some processes unfold slowly, altering conditions over decades or centuries. Others occur abruptly, triggered by events rarely witnessed. Without continuous observation, distinguishing between background variation and significant change becomes difficult. Models attempt to bridge this gap, but rely on assumptions that must be tested gradually as new data arrives. What remains unknown is not a void, but a layered complexity awaiting clearer resolution. Each descent reveals hints rather than conclusions. Each dataset refines boundaries without closing them. The deep ocean retains much of its autonomy, operating beyond the cadence of exploration that reaches it intermittently. This state of partial knowledge shapes how science advances. Progress unfolds through patience rather than accumulation alone. Unknown terrain, unseen ecosystems, and unmeasured processes are acknowledged as active components of understanding, not simply gaps to be filled. They form a quiet backdrop to discovery, reminding us that proximity does not guarantee familiarity. Beneath the surface, much continues unchanged by observation, existing in patterns still forming, still unfolding, beyond the reach of current certainty. Understanding the deep ocean is challenged not by a single obstacle, but by the way its systems interlock. Complexity does not sit neatly in layers that can be examined one at a time. It accumulates, overlaps, and feeds back into itself. Physical structure shapes motion. Motion alters chemistry. Chemistry guides biology, and biology in turn modifies the physical environment. Each element exists within the influence of the others, forming a system that resists isolation. Motion is constant, even where the water appears still. Currents shift gradually, transporting heat, nutrients, and dissolved gases across vast distances. These movements are shaped by temperature differences, seafloor contours, and Earth's rotation, yet they also respond to subtle changes that are difficult to predict. Flow patterns bend around obstacles, split, and rejoin, creating pathways that rarely repeat exactly. This motion influences where life can persist and how materials accumulate or disperse. Chemistry adds another dimension to this interplay. Pressure alters how gases dissolve, how minerals react, and how energy moves through the system. Chemical gradients form and dissolve as water masses mix, creating localized conditions that may exist only briefly or persist for long periods. Small changes in composition can shift biological viability, altering which organisms thrive and which fade. These chemical processes are neither uniform nor static. They evolve with depth, time, and movement. Biology responds to these physical and chemical settings while also reshaping them. Microorganisms mediate chemical reactions, accelerate mineral formation, and influence nutrient cycling. Larger organisms modify sediments, redistribute matter, and introduce structure through their presence. Life in the deep is not merely a passenger within the system, it participates actively, reinforcing some processes and damping others. Its influence may be subtle, but over time it becomes significant. The absence of a single controlling variable makes prediction difficult. No singular measurement explains behavior across regions or depths. Temperature alone cannot describe circulation. Chemistry alone cannot define ecosystems. Biology alone cannot explain distribution. Each parameter gains meaning only in relation to the others. Removing one from consideration simplifies models, but also distances them from reality. This interdependence challenges intuition. Human understanding often seeks dominant drivers, clear hierarchies of cause and effect. In the deep ocean, influence is distributed. Causes branch and recombine, producing outcomes that vary with context. Similar conditions can lead to different results depending on timing, location, and interaction history. The system behaves less like a machine and more like a network, adaptive and responsive. Because of this, knowledge advances slowly. Insights accumulate through convergence rather than discovery alone. Patterns are recognized when multiple lines of evidence align, drawn from physics, chemistry, and biology together. Even then, conclusions remain bounded, aware that unseen interactions may still operate beyond measurement. The ocean resists understanding not through concealment, but through richness. Its processes do not simplify themselves for observation. They continue in layered coordination, indifferent to clarity. To study such a system requires patience, acceptance of partial views, and a willingness to let complexity remain unresolved for long stretches. In that resistance lies both the challenge and the quiet fascination of the deep, a reminder that some environments are understood not by control, but by sustained attention over time. The deep ocean remains positioned just beyond the reach of ordinary scientific rhythm. While many fields operate through continuous measurement, rapid iteration, and frequent verification, work at extreme depth unfolds differently. Observation there is episodic rather than constant, separated by long intervals of preparation, deployment, and recovery. The boundary is not geographical alone, it is procedural, shaping how knowledge is gathered and how quickly it can mature. Most science advances through routine access. Laboratories can be revisited daily, instruments recalibrated, and hypotheses adjusted in near real time. The deep ocean does not allow this cadence. Each encounter requires specialized equipment, coordinated vessels, favorable conditions, and significant time. Once a mission concludes, months or years may pass before the same site is reached again. This spacing alters the relationship between question and answer. Technology defines much of this separation. Tools capable of reaching great depth must withstand pressure, corrosion, and isolation for extended periods. Their complexity limits how often they can be deployed. Repairs are slow, testing is meticulous, and failure carries high cost. Unlike systems used in surface science, these machines cannot be modified easily between uses. Design cycles stretch outward, slowing responsiveness. Even when technology performs as intended, its reach remains narrow. Instruments operate within constrained windows of time and space, collecting data that reflects specific conditions rather than continuous states. These snapshots are valuable, but they do not replace sustained presence. Patterns must be inferred across gaps, stitched together from isolated moments. Daily science thrives on accumulation. Deep ocean science relies on patience. This patience shapes methodology. Researchers frame questions that can survive long delays between observation and analysis. Studies are designed to extract maximum insight from limited contact. Results are interpreted cautiously, aware that follow up may not be immediate. Progress unfolds through careful extension rather than rapid correction. The boundary also influences integration. Discoveries from the deep often take time to filter into broader scientific discourse. Their rarity demands validation across independent missions, sometimes years apart. Consensus forms slowly, built through repetition rather than immediacy. This separation protects accuracy, but it also reinforces distance from everyday scientific practice. Patience becomes a defining resource. It guides investment, shapes expectation, and calibrates ambition. Advances occur not when access improves suddenly, but when persistence accumulates. Small refinements compound, enabling deeper dives, longer deployments, and more reliable instruments. Each step is incremental, yet meaningful within a landscape that does not reward haste. The boundary remains not as a failure of curiosity, but as a reflection of proportion. The deep ocean operates on scales that resist compression into routine. Its study progresses through endurance and restraint, accepting that proximity does not ensure familiarity. Science continues to approach this boundary steadily, guided by patience that respects both the limits of technology and the nature of the environment itself. The ocean remains the closest unexplored world, not because it is hidden by distance, but because it endures beside us in a different state of access. Its surface is familiar, traced daily by ships and weather, visible from coastlines that frame human history. Yet beneath that surface lies a realm that unfolds on its own terms, largely untouched, operating beyond the rhythms of ordinary observation. This proximity gives the deep a unique character, one shaped by nearness without intimacy. Familiarity softens perception. Water appears uniform from above, shifting gently with light and wind. The vastness beneath is easy to overlook when daily life intersects only with the uppermost layer. Depth transforms this apparent simplicity into something layered and expansive, extending downward into environments governed by conditions rarely encountered. The transition is not abrupt, but gradual, unfolding meter by meter until the rules governing life, motion, and matter change completely. This contrast allows mystery to coexist with routine. Ports, coastlines, and fisheries rely on the ocean daily, integrating it into economies and cultures. At the same time, entire regions below remain scarcely observed. Knowledge advances along the edges, revealing patterns while leaving interior spaces largely undisturbed. The ocean becomes both known and unknown simultaneously, a presence that supports life above while remaining elusive below. The deep does not announce itself as unexplored. It does not resist through barriers or distance. Instead, it persists quietly, continuing its processes without regard for observation. Geological reshaping, chemical exchange, and biological adaptation proceed continuously, regardless of whether they are measured. The ocean's mystery is not performative, it is sustained through continuity. This endurance shapes how exploration is understood. Discovery here is not defined by conquest or arrival, but by gradual alignment between tools, patience, and environment. Each glimpse is partial, each insight provisional, yet collectively meaningful. Progress emerges through accumulation rather than resolution. The deep ocean remains unfinished, not awaiting completion, but accommodating understanding as it develops. Its nearness serves as reminder rather than challenge. It illustrates that unexplored does not always mean distant, and that familiarity does not guarantee comprehension. The most profound unknowns can exist alongside daily experience, integrated into routine while retaining depth that escapes summary. In this way, the ocean reframes the idea of frontier, not as a boundary pushed outward, but as a depth approached inward. It invites attention rather than pursuit, persistence rather than acceleration. The mystery it holds remains steady, shaped by complexity that does not diminish with proximity. Earth's closest mystery does not lie beyond the sky, but beneath the surface that surrounds continents and connects climates. It remains present, patient, and largely unchanged by observation. As science continues its slow engagement, the ocean stands as quiet testament that exploration is not always about reaching farther, but about recognizing how much remains unseen within reach, waiting not to be discovered all at once, but understood over time.